welcome back. So, let us start. Now, today we will talk about the phi to the power 4 theory in the context of Euclidean d-dimensional space. The interaction, the action term then captures another interaction term involving the coupling constant, and the action can be written in the form that is given in the first equation with the red box representing the interaction term. We then, as in the case of 0 dimensional theory, we expand this interaction term on the premise that the coupling is small as a power series in the coupling constant, and we obtain an expression for the generating functional and the normalization in the interaction theory as the expressions given in the red box and the green box respectively. This is pretty much the situation that we encountered in the 0 dimensional field theory, and then we define 2n point green functions in terms of h2n and 0 h2 h0. This again follows what we did in the 0 dimensional case. The Schwinger-Dyson equation for Zj was obtained in the form given in the red box, and for the phi 4 field it takes the explicit form given in the green box at the bottom of your slide. Schwinger-Dyson equation for the field operators can be in either of the forms 1 and 2, and for the phi 4 field we have this expression which is again given in the green box right at the bottom of your slide. So, and the Feynman diagrams which led us to the Schwinger-Dyson equation given in the green box here for the phi 4 field in the case of 0 dimensional theory are reproduced here for the sake of continuity. So, all the results so far that I have enumerated were delivered and discussed in the context of 0 dimensional field theory in an earlier lecture. Now, we take up this situation in the case of Euclidean d-dimensional space. In the case of Euclidean d-dimensional space, our first step obviously is to obtain the Schwinger-Dyson equation for the propagator. We consider a field function entering through an external leg at the space time point x or Euclidean point x, and what are the possibilities or what are the various situations or scenarios that this particular field function can encounter on entering through an external leg are depicted on the right hand side of the equality. The first diagram represents the fact that the incoming field gets propagated to a field new field phi at the space time point y phi y, and then it jumps into or then it encounters the source j y. Now, because the propagator, as I mentioned in a previous lecture, the propagator singles out a particular y as the outgoing field, we need to sum over all possible values of y to correspond to the situation on the left hand side of your equality. Then the other situation that can arise is that after propagating to the space time point y, the fields the new field phi y encounters an interaction 4 point vertex, and each of these 4 point vertex then has the possibility of going back into the blob that is there on the left hand side. In other words, it could further encounter the same situation that the field entering at the point x had encountered. In other words, it could again encounter and face or propagate to another space time point and then encounter a source there, or it may encounter more 4 point vertices and so on. Each of these 3 vertices, outgoing vertices or 3 outgoing lines rather, I am sorry, emerging from the 4 point vertex could lead to any of these situations. Then there could be a situation that again the summing over the outgoing field has to be done, and then there could be a situation where the phi x gets propagated to a new space time point y, and then again it faces or it encounters a 4 point interaction, and post interaction after interaction the field two branches emerging from the vertex again go into the same blob, while one branch goes away to another blob to another situation where it faces either another 4-point vertex or it faces a source. So, that is the interpretation of the first diagram of the bottom line, and similarly the second diagram of the bottom line can be interpreted, where all the three outgoing lines emerging from the 4-point interaction rejoin or reunite into the same blob. Now, we translate that to a Schwinger-Dyson equation. The translation is almost absolutely parallel to what we had for the 0-dimensional case, except for the fact that there is an additional summation over y, and this summation over y translates to an integral in the continuous form, and therefore, in the Schwinger-Dyson equation we have an additional integral, as you can see, integral with respect to the y coordinates of the propagator, and then we have this representation of each of the 4 diagrams that we discussed just now. Now, we come to the explicit form of the propagator in the context of the current Euclidean space. Recall that we had worked out the propagator as to the expression that is given in the first equation on your slide in the previous lecture. This was precisely the expression that we obtained in the continuous case of the d-dimensional Euclidean space. Now, we try to obtain an explicit expression for that, a closed form expression for this to the extent possible. Now, if you look at the expression in the red box in the top equation, this expression in the red box in the top equation can be represented by an integral that is given in the blue box in the second equation on your slide. Integral between 0 to 1 and 0 to infinity, integral between 0 to infinity dt exponential minus t k dot k plus m square. If you perform this integral, you get precisely 1 upon k dot k plus m square, which is the expression in the red box. So, that being the case, we can replace the latter by the former. That is precisely what is done, and now we do the integration. We take the dt integral in to separately, and the remaining integral now becomes clearly a Gaussian integral, and that is easily performed. The expression in this black box purple box is the Gaussian integral, and this Gaussian integral can be easily performed to obtain the expression in the green box. So, what we have now is the last equation with the expression in the green box representing the solution of the Gaussian integral product of the Gaussian integrals that we have in the second last equation. The product running from j to d is nothing but the mod of x square, which is what it is substituted in the second equation, and the rest of it is as it is, and we get the expression in the second equation on your slide, which can be written in terms of the Bessel functions, modified Bessel functions of the second kind. This expression here k m mod x is the modified Bessel function of the second kind. This modified Bessel function of the second kind has a representation, an integral representation given at the bottom of your slide here. So, just a recall, z here is equal to m mod x, as you can see in the previous slide. It is the modified Bessel function of the second kind of m, argument is m mod x, and here the argument is z. So, z is equated to m mod x, and the expression for the propagator is given in the small box here at the right hand side of your slide, and the integral representation of the modified Bessel function is given right at the bottom of your slide. And as far as the normalization is concerned, the normalization of the propagator is straightforward. Integral pi of x with respect to the Euclidean volume works out to h upon 2 pi d integral d dx integral dk exponential, this is the expression for the propagator, and if you insert there the delta functions, that the exponential I k x becomes 2 pi to the power d delta d dimensional delta of k, and when you do the k integration, the d dimensional delta goes, and what we are left with is h upon m square, because k when you do this integral, the k term vanishes, and the k term vanishes, the delta term vanishes, the 2 pi cancel out, and we are left with h upon m square. So, that is the normalization in every dimension. Now, we explore the behavior of the propagator in various extreme situations. For very large values of z, the integral is dominated by the region around u is equal to 1. Recall that u is equal to 1 represents the stationary point or the saddle point, and the integral in that situation is given by the expression in the green box. It is clearly obvious that the as z tends to infinity, the propagator decreases exponentially, falls exponentially. So, this is the large scale behavior or large distance behavior of the propagator. You can also obtain this expression more explicitly, because the pi x, the propagator is a solution, is a green function of the Euclid Kleene-Gordon equation in Euclidean space, and therefore, we have this equation here which I have underlined, and this equation in the limit that delta x tends to 0, the sources tend to vanish, and therefore, we have the expression Laplacian minus m square of pi x is equal to 0. Writing out the Laplacian in terms of the explicitly in terms of spherical coordinates, we get the expression that is at the given in the green box, and further as r tends to infinity or r increases, r becomes large, the second term, that is the d by dr term, vanishes, and we are left with a straightforward differential equation del d square upon dr square minus m square is equal to pi r, with the explicit solution pi r is equal to exponential plus minus m r. Obviously, the propagator cannot grow with distance, therefore, the plus sign is discarded, and we have pi r is equal to exponential minus m r, which again shows that the propagator decreases exponentially as time increases, as distance increases. I am sorry. Now, for small z, we may for the expression u plus 1 upon u, we may substitute it by u, and we arrive at the two expressions k 0 z is equal to log 1 upon z for that is obviously for d equal to 2 dimensional case, and k alpha z for d greater than 2 is 1 upon 2 into 2 upon z to the power alpha gamma function of alpha. Now, the first one holds for d equal to 2, and the second expression for the modified Bessel function holds for d greater than 2. Clearly, and this leads to the expressions for the propagator given in the red box for d equal to 2 and given in the green box for d greater than 2, that is greater than equal to 3. Therefore, for small distances, the propagator seems to have a pole. Now, the expression for the if you look at it carefully, this the first part, the prefactor of mod x to the power 2 minus d is a quantity which depends on the dimensionality, and then it has mod x to the power 2 minus d. Clearly, as d tends to as x tends to 0 with d greater than 2, the propagator approaches a pole. Therefore, in the case of small distances, the propagator behaves as a pole for d greater than 2, d greater than 2 limit x tending to 0 pi x approaches infinity for d greater than 2. What happens for d equal to 2? For d equal to 2, the propagator is given by this expression minus h bar upon 2 pi log of m mod x. Here again we encounter divergences as x tends to 0. The divergence in this case is logarithmic divergence or log divergences, and this is called infrared divergence. The previous divergence for dimensions of 3 and greater than 3 are usually called ultraviolet divergences. Of course, for d equal to 1, when we have only the time variable, that is traditional quantum mechanics, pi of t is equal to h bar upon 2 pi exponential minus m mod x, which is finite at x equal to 0. So, the traditional quantum mechanics, which is 0 plus 1 theory, quantum field theory, is equivalent to 0 plus 1 quantum field theory. The issue of divergences in the propagator does not arise. So, to conclude here, for d greater than equal to 2, pi 0 is divergent, it tends to infinity, where pi 0 is the expected value of phi square x at the same space time point. The expected value of phi square x is phi x into phi x, both of them being at the same space time point, the product of equal position and equal time of field operators, and this product or this expected value tends to diverge for dimensions greater than equal to 2. The degree of divergences increases with the dimensionality. This is ultraviolet divergence, and for d equal to 2 we have infrared divergences, but the divergences nonetheless manifest themselves. Now, we look at certain examples of Feynman diagrams in the current theory. The first one is quite simple. The lowest order no loop 2-point function that is given by the expected value of phi x1, phi x2, we call it a1, and that is just a straight line joining x1 and x2 as a Feynman diagram, and that represents the propagator pi x1 minus x2. Then we look at the lowest order contribution to a 4-point function. A 4-point function is given by the expected value of phi x1, phi x2, phi x3, phi x4, and this is obtained by writing down all Feynman diagrams with 4 external legs and no source vertices. 4 external legs and no source vertices. There will be 4 such diagrams, as you can see on this slide. The first diagram, second diagram, third diagram, and then we have the fourth diagram. First diagram, second diagram, third diagram, and the fourth diagram. The main diagram in the diagrams 1, 2 and 3 simply evaluate to products of the propagators. For example, the first diagram evaluates to the product of the propagators between x1 and x2 and the propagator between x3 and x4. Similarly, the second diagram evaluates to the product of the propagators between x1 and x3 and the propagator between x2 and x4. And the third diagram as well. However, in the case of the fourth diagram, because we have a vertex here, we need to the factor of lambda 4 comes into play, and this vertex evaluates to minus lambda 4 upon h, and the propagators evaluate as usual corresponding to the 4 lines. We have 4 propagators. But then another important thing is that because y is we are not talking about space time points in d dimensions, we need to integrate over all values, all possible values of y, and that is why the y integral appears here. So, in the fourth diagram there will be a y integral here because of the existence of the vertex at the point y, and secondly the vertex also evaluates to minus lambda 4 upon h bar. Now, we have another interesting Feynman diagram. This is a diagram in the phi 3 theory. It has 2 vertices, as you can see, vertices at the point y1 and vertices at the point y2. There are 3 point vertices, 2 3-point vertices which combine together to form a loop, and therefore, each of them evaluates to lambda 3 upon h bar, and therefore, we have lambda 3 upon h bar square. Of course, 1 by 2 is the symmetry factor which allows for the flipping of the leaf, and we also have integration over y1 and y2 both, because these are two vertices in d dimensional space time, and therefore, they need to be integrated over. And and also note that because there are two lines joining y1 and y2, we have the square of the propagator between y1 and y2 within the integrand. Now, we introduce wave vectors or Fourier variables. So far, you see, we have considered phi x, that is, the independent variables have been field values at every point of space time. We have considered the field values at every point of space time as the independent variables. Now, we consider phi k as the independent variable, that is the modes as the independent variable. Modes, or they are also sometimes called wave vectors. They are intimately related to momentum, but they are basically the Fourier transforms of the field functions in space time, and therefore, they are given by the expression given in the green box. In other words, what we are simply doing is we are decomposing the field function phi x in terms of its Fourier components of Fourier modes. So, phi x is represented by its Fourier transform, and the inverse is given by the expression in the green box. Similarly, we do the same, we decompose the source j x also in terms of its Fourier modes as the expression given in the blue box, with the inverse which is also given at the bottom or the second equation in the green box. Now, there are certain advantages of using modes over the usual space time prescription. For the free theory, the various modes are independent of one another in contrast to the fields at different space time points. The fields at different space time points, even in the case of free theory, are not independent of each other and they are correlated. However, for the free theory, the modes at different the various modes of the field function are independent of each other. Then momentum conservation is a universal law, and the momentum conservation law can be directly applied in momentum space or in Fourier space. Actual measurements in experiments are usually return the momenta of interacting particles rather than the space time points at which the interaction takes place. So, these are three fundamental advantages which accrue on using the modes or the Fourier variables instead of the space time variables for depicting, for representing the fields. Some examples of mode space computation computations of Fourier space computations. In the position space, we have, for example, the 2-point function is given by the expected value of phi x1 and phi x2. This is in the position space, and this is the expression for the propagator also. In the mode space or in momentum space, we will have phi k1, phi k2, and that will be by using the relationship between k1 and x1 and k2 and x2, the Fourier transforms of each other, we get integral over x1 integral over x2 exponential minus I x1 k1 minus I x2 k2 phi x1 phi x2. We have simply transformed x1 and x2 from into their Fourier transformed variables k1 and k2. Now, phi x1 phi x2, as I mentioned earlier, is nothing but the propagator, and the expression for the propagator is given at the right at the bottom equation of your slide. So, phi x1 phi x2 is the expression for the propagator which is here, and we substitute this expression for the propagator phi x1 phi x2 into the equation. Let us call it equation number 1. In other words, what we are doing is we are substituting the expression for phi x1 phi x2 from equation 2 in equation 1. And what do we get? This is what we have from when we do the substitution, what we have is we get another third integral, and this third integral comes from the expression for the propagator, that is in equation 2, and the rest of it is carried as it is into this equation. Now, if you look at it carefully, we get certain delta functions minus I x. We are looking at the exponents of the exponential. Minus I x 1 k 1 you have here, and I k x 1 you have here. So, these two expressions combine together and give us a delta function over k minus k 1. Similarly, the second delta function is k plus k 2. So, we have two delta functions here, and we have an integral over k. When we do the integral over k, the delta function goes away and we replace k everywhere with k 1 when we integrate over the first delta function, that is k minus k 1. This gives us k equal to k 1, and we replace everywhere k equal to k 1, and we get this expression. Now, we look at the second example, that is the example that is of A2, that is the 4-point function, the lowest mode. A2 is given by the expression that you have on the slide. We shall first analyze the last term, the fourth diagram that involves a vertex, 4-point vertex. We shall first analyze this expression, and then we will incorporate the rest of the evaluation, which is elementary, and we get the full expression for the 4-point green function. Let us look at the fourth diagram, that is we are evaluating this diagram, the fourth diagram. Let me mark it as 4. Right. Now, we look at the 4-point function, and we look at the lowest order contribution in the 4-point function. The expression in position space is given at the right hand side of your slide. We look at the expression for the same thing in momentum space in Fourier space. So, this is the expression. We first examine the fourth diagram, that is diagram number 4 given here, and we look at the outcome of the fourth diagram, representation of the fourth diagram in momentum space in Fourier space. So, the 4-point function is given in terms of the expectation values in position space of phi x 1, phi x 2, phi x 3, phi x 4, which is given in in terms of the propagator. This expression is shown in the red box at the top of your slide. Transforming it into Fourier variables, we have the expression which is given at the bottom of your slide. The expected value of phi k 1, phi k 2, phi k 3, phi k 4 connected. This is the 4-point function with representation in the Fourier space. Now, this is what we have from the previous equation. The first equation is what we have from the previous equation, but the expected value of phi x 1, phi x 2, phi x 3, phi x 4 in terms of propagator we have already seen in the previous slide. It is there. Here it is, the equation in the red box. We use this expression and we write the 4-point function in momentum space in terms of the propagators of position space. And thereafter, we use these explicit expressions for the propagators. We substitute each of these propagators with the explicit expressions given at the top of the topmost equation on the slide, and we get the expression in the second equation on the slide. This equation obviously can be transformed to using the methodology in the earlier case. We have several number of delta functions emerging from the coefficients of the exponentials, and when we integrate over these delta functions, in other words we do the dq1, dq2, dq3 and dq4 integrations, the expression that we end up with is the expression given in the green box on this slide. Right, we will continue from here after the break. Thank you.